So before we start, how about a survey? So who's had coffee? Hands up, come on. Who's had? Okay, I should have said who's not had coffee. Okay, so keep your hands up. Who's got a PhD or a master's? More. Okay, should have said that first. Okay, so okay, and hands still up. Who's working on deep learning of that set? Okay, should have started with that. Silly. Okay, so no excuses then. Okay, so let's have a pop quiz. So I'm going to give you 5 seconds to answer, the people who had their hands up. And I think this is the most important question in deep learning, so that's why I'm giving you 5 seconds. So the question is, what is the opposite or inverse of abstraction? I'm going to count. That's a 5, 4, 3, 2. Sorry? Specification? No. Sorry. It's kind of interesting, but no. An example? VCs. Give this guy a blank check. He's almost there. So the answer to this, the correct answer is synthesis. Now, I'm not going to derive that now, but that's the answer. And this is a kind of a yin and yang thing. Now, before we go into the actual talk, a bit more rhetoric, because that's fun. So deep neural networks are usually interpreted in 2 main ways. The first would be universal function approximation, and the second would be probabilistic or information theoretic interpretation. So the former of these is concerned with the nature of the function, and the latter is concerned with the utility of the function. Notice I'm emphasizing the function. So Bruce Lee, of all people, once said, "Don't be distracted by the hand that points at the moon." And in this case, I'm referring to the function being what we're looking at. So we can do a thought experiment to get a sanity check on this question about abstraction, which is what we want to do in deep learning most of the time, and synthesis. And the thought experiment goes like this. So can we have a negative number of apples? I don't want hands up. The answer is no, obviously. It's rhetorical. So in the real world, based in physics. Okay, so we need a magnitude. We need a positive number, or maybe at least 0, of apples to make sense in the real world. And this is how we get between abstraction and synthesis. This is a yin and a yang, if you like. So moving on to some actual more interesting stuff, quite slowly. I want to pose a question because deep learning is full of pretty vague terms, and it would be nice to know what we're talking about. So what's learning, and how do we get from machine learning and this, the perspective of that to what the brain does and what we want to do? So I would say maybe we can say the weights are like synapses, and we're going to optimize the weights to do something. And I think this is a pretty good brain deep net analogy. Okay. Yeah. So, hang on a minute. No, I'm going ahead of myself here. Way ahead of myself. Need to go back. Okay. I'm going to literally go back. So, going back to the rhetoric we need to build on. Although it's very attractive to interpret deep nets in terms of the universal approximation or information theory or inference, which is useful, but when it comes down to it and you strip all that away, you have discrete signal processing. So deep nets are basically linear filters, nonlinear activation functions. So the linear filters are good because they're selective of features. We like features. And the nonlinear activation functions are good because they act as demodulators on these features. So they give us some magnitudes. Now, demodulation is, I guess, by definition, or my definition, is where we take the magnitude of the variance of a feature. So it can't be negative, and we can't have negative apples. So that's good. And we do this in signal processing with rectification. So this is where the sanity check becomes nice and easy. If we're going to abstract, we need to get magnitudes, and we need to think about going backwards being the opposite end of the same problem. So, okay, now I'm just going to try and keep myself in a straight line here. So again, I'm going to restate the last bit. If we say that in machine learning we're going to optimize our weights, and that's like optimizing synapses for learning, then we have a pretty good analogy between the brain and its neurons and machine learning. But if that's learning, then what's memory? And in the brain, in neuroscience, I think we're pretty convinced that memory is also in the synapses, and if that's true, then it would also be in the weights of a deep net. But this seems to be where we depart from a kind of useful analog. So, and this morning we've had plenty of talks, especially Alex Grace was telling us about NTMs, which is similar to LSTMs that we've been seeing a lot of work done on. Memory is, we have weights, yeah, we learn those, and we have memory, but what's that? That looks like storage. So this way is kind of programming computer science software. But the brain is kind of, I don't see that argument for the brain. So we have, in the brain, I think it's more likely we have memory and learning in the weights somewhere. So this is a big question, because this doesn't seem to be, it doesn't seem that memory emerges from learning in the weights of a deep net. And another related question is, why do we practice when we're learning something with our brains? Or what's practice? Why is it necessary? And we could maybe kind of find an analog in gradient descent or something like that, but it seems very important to us in our brains, but it's pretty difficult to explain what it means for machine learning. So, going back to the yin and yang of abstraction and synthesis, we have two types of learning. We have abstraction and synthesis. So this gives us, if we believe that the memory is in the weights, gives us two types of recall, which being abstraction, so recalling a class for an image, or synthesis, recalling an image for a class. This is kind of associative memory. So if we take that together associatively, then maybe we can learn from memory. And maybe we can take these sort of definitions and do something useful with them. So let's say we say learning is optimization, and we're going to use stochastic gradient descent because that's what we sort of know. And we're going to say that memory might be recalled via abstraction or synthesis, being the yin and the yang pair. So maybe we can call practice something like the statistics of what we learn. And what this leads to is another question which seems even weirder, which is, what if we learn from memory? How the hell do we define that? What's going on? And the way to unpack this is to imagine that we have two really kind of different mechanisms, both from signal processing, both inverse. And one of them would be remembering an abstraction, one of them remembering a synthesis. And then maybe if we have that kind of memory, then we can have everything in memory that we would need to train a neural network in memory. So maybe we wouldn't need a training set anymore because we'd know it. So then we have an interesting kind of yin-yang architecture. So up the top, we have a classifier. This is an abstractor, basically. And we take an image, we feed forward, and we're going to train this to predict a class. And at the bottom, we have the opposite thing, where we're going to train a synthesizer on a class to synthesize the image. Now, the yin and yang of this is interesting because obviously we're not doing abstraction at the bottom because it's a synthesizer. So what's going on? And the answer here is that the abstraction happens on the way down because we're doing backprop. So the backprop is abstracting the error and pushing it down. And at the top, we're abstracting the image up to a class, and we're backpropping. That's synthesis. So we're synthesizing our weights, and here, this is a Yinyang thing. So if we take these two things together, and we say we're going to go around in a loop, and we're going to have our training set in memory, and we're going to learn from it, and we're just going to go around like that. So we take these two guys, and we put them in a perpetual loop, and we pick a random class. And the synthesizer spits out an image, which it remembers, synthesizes an image, and then we use that image and the random class we picked, and we train both of them on that as training data. And then we go round and round, and probabilistically with a uniform distribution of this class selection, we keep going round and round, and this is a kind of perpetual memory. That's my argument. So, more specifically, this is a MNIST, sorry about that. Hands up, who's done MNIST for like 10 years? Anyone? Okay, fine. So the rest of you, MNIST is great. So we know what the classifier does with MNIST. This is an associative classifier, so these are arbitrary classes. We just take some digits, and we assign them to classes arbitrarily. But nonetheless, the classifier makes those classifications and learns them. On the other side over there, we have what gets recalled from the synthesizer. So we're training the synthesizer with the same data, but to synthesize. So this is what comes out of the network from some experiments. So, yeah, this is a lot slower than I thought it would be. So here's an experiment. We have these pair of neural networks, yin and yang, and we first train them to convergence with standard non-batch stochastic, or let's say online stochastic gradient descent, and they converge, and they know exactly which classes go with 50 images, MNIST images, digits. These are not the digits, these are just arbitrary associative classes, but still, it remembers how to classify these 50 and also how to synthesize these 50 from their associative classes. So we go into our perpetual stochastic gradient descent, which is our loop, where we're just randomly recalling, training both of the networks on that, and we keep going along for 1,000 iterations of that, and nothing happens. That's cool. And we're quantifying our recall error for the classifier, because that's easier to measure, for the 50 things we trained it for to convergence. And the perpetual nature of the perpetual gradient descent just holds on to that fine. Now we also have a test set, we have an error computed on 25 new classes it hasn't seen. It's never been trained for. They're in its layers, in its paradigm or in its regime, but they've never been trained. So the error is pretty bad, i.e. it's completely useless. But at the point of 1,000 iterations, we start, at the same time as doing this perpetual stochastic gradient descent, we throw in randomly selected steps of stochastic gradient descent for the test set, which is new, which is never seen before. Now we haven't got the training set anymore because we threw it away and we have it only in memory. So we're keeping that going perpetually in our randomly selected, keep it alive, use it or lose it kind of thing. And we're adding in the new ones. And what we see first is the old stuff takes a bit of a hiccup, and that's the blue line. But after a pretty short period, it more or less recovers, keeps itself going on. And the red line is just the whole set error. So that's the typical classifier error. But what we see is that basically, if we put something new in, we can add it to the training set because the training set's in the memory. So we can actually think about deploying neural networks and having them just add stuff to what they know. And, after 3,000 iterations, we stop doing any new learning, and we just hold on to it. So this is what I mean by perpetual. It's not perfect, but close enough to be interesting. So this, coming back to practice and having a stochastic gradient descent, which is based on actual individual learning, individual training examples, we can actually start to think, okay, what if we practice really hard with 25 in red, and we practice kind of medium in green, and then some of them we hardly practice at all? And the answer is that the test error follows. It's cumulative. I mean, maybe mathematicians are not surprised by this, but I think this is pretty new as a way of thinking about it. And more interestingly, although I can't see an application right now, if we, instead of training from scratch by practicing really hard on some stuff and not so hard on other stuff, then maybe if we take a really nicely trained pair of these Perpetual Learning Machine Yinyang networks, and then we have them recall, so that they're just going around learning from memory in this perpetual stochastic gradient descent. They don't have a training set anymore. There's no outside influence, no stimulus, as it were. They're just recalling from memory stuff with different a priori statistics and learning that. So instead of randomly, uniformly selecting during perpetual stochastic gradient descent, we're going to have probabilities. And I guess this is how often do you recite Shakespeare versus Bruce Lee. So in this case, the things which we don't recall in this perpetual loop and don't train on start to fade away, and we can call that forgetting. And the things we recall kind of not that frequently get a bit worse, and the things we recall all the time, well, use it or lose it. So I'm calling this a perpetual learning machine. I'm sure there's analogues and equivalents, but the point here is that the motivation for this is to extend the deep neural network architecture so that it will do something more dynamic and more brain-like. And maybe forgetting is not really cool if you've got a self-driving car, but unless you're an insurance company, so come and talk to me afterwards. But here's a kind of basic marketing summary of this. So the brain definitely learns as it goes. It doesn't have a training set which it has to add to and go back to random weights every single day. And we do have this from this Yinyang kind of setup. We also have something that's kind of consistent with using practice to drive what we prioritize in our learning. And we also, if we choose to have this, then we maybe forget stuff that's not useful. And in terms of a finite capacity that's in the weights of a deep neural network, maybe that might be useful if holding everything in memory is not a great idea. So trying to interpret this a bit more broadly in terms of marketing, maybe. So this is a sort of paradigm shift because right now you have deep nets which get gorilla faces wrong embarrassingly. But maybe the users could help them with that, and instead of going back to the servers and crunching for like 2 years, maybe the user would just go, that's not gorillas. And maybe this is more useful to adapt to the context of what's going on, what a neural network might be used for. And maybe it'd be nice to just keep up with development, so when you buy some product with a neural network in it, it's not out of date and redundant maybe, or just wrong the next day. So this is maybe a bit unpredictable, and maybe we need education or something like that for these things. But if it forgets, if it learns stuff that you seem to care about, or it seems to care about, maybe that's useful because it might give us some AI that feels a bit more human. And it would be cool if we could invest ourselves in neural networks and train them and educate them and be their daddy. So, yeah, that's basically it. A couple of references for those with binoculars. And that is the slightly shambolic end.